I guess I'll get started. Just a couple things. One is I just put a poll on Piazza. I meant to put this in PSET 1 itself. Please let me know like how much time you spent on PSET 1. I want to monitor how much time things are taking. Another thing is we did have a scribe for September 30th, which is a week from Tuesday. We no longer do. So please, someone, take that slot. If you have a later slot and want to switch and be earlier, that's also very good. Another thing is our videographer has asked if anyone wants the board shot differently or anything in the videos, please let us know. Okay. Thanks. Okay. So and also I fixed the two bugs, the off by one and cuckoo hashing, and the lemma I didn't actually prove for power of two choices is fixed in the notes, so you can go read it if you want. Okay, so we're going to start a different topic today. We're not going to operate in word RAM anymore, at least for now. We're going to look at amortized analysis. Okay, and we're going to start off with data structures. And the two we're going to look at are Fibonacci heaps. Well, we'll look at something else right before Fibonacci heaps, another heap, and we'll also look at splay trees. Okay. Good. So I think people who took 124 here, like people who were undergrads here, I guess you've seen some amount of amortized analysis. Well, at least one bit of it when we did union find. Okay, but we're going to say a little more. So what's the idea behind amortized analysis? So amortization, or amortized bounds. We'll say, like, suppose our data structure supports some number of operations. Operations, A, B, C. Then we say the amortized costs of these operations are, let's say, T sub A, the time for A, T sub B, and T sub C, if any sequence of NA A operations and NB B operations, etc., and NC C operations takes time at most NATA plus NBTB plus NCTC. Okay. So the idea is, so usually we talk about worst case running times for, say, data structures. So a balanced binary search tree, a red-black tree, takes log n time to do a search. Okay. If we say that it takes log n amortized time to do a search, it means that if we do n searches in a row, or some k searches in a row on a data structure of n items, then it should take us at most k times log n steps total. So some of these operations can be expensive. Some of them can even take linear time. But as long as the sum of all the time we spent is at most as this, then we say that that's our amortized complexity. Okay? And we're going to see some examples. Okay. And a common way of proving amortized bounds is what's known as the potential function method. And we'll see this with splay trees sometimes. This can get a little, sometimes it can be weirder than other times. So common way to prove amortized bounds is via the potential function method. Okay, so what is that? So we define a potential function call it phi. It maps a state space of our data structure okay, into non-negative reals, let's say. I don't know if that's the usual notation. Somehow I feel like it should be a subscript. Okay, anyway. Okay, and also phi of like an empty data structure is 0. Okay. And so let's say that we perform k operations with costs, actual running times T1, Tk. So here I don't mean we support k different types of operations. I mean, suppose we actually have a sequence of operations on our data structure, for example, k insertions or k searches or something. And the actual running time of each operation, of the ith operation, is Ti. Okay. And the states of the data structure are S0 before we start any operation, S1 up to Sk. So Si is the state of the data structure after the ith operation. S0 is before we do anything at all. Okay. So our amortized cost, okay, our amortized cost of an operation is, we define it to be, the actual time plus the potential difference. Okay. And why does this make sense? So the total amortized cost sorry, this is not the this is not what I wanted to say. I guess what I wanted to say is, so this is what I define the amortized cost of a sequence to be. So I want to say we'll show that this is the case, is bounded by, let's say. The amortized cost of one given operation is bounded by this. And why is that the case? Well, let's sum this over all operations. So the total amortized cost is, we're bounding it by the sum over I, Ti plus the difference in potential. But this is a telescoping sum, and all we're left with is the sum of the actual costs plus the final potential minus the original potential, which was 0. Right? If we started with an empty data structure, it's 0. Which is certainly at least the actual, remember that phi maps into positive numbers. So this is at least the actual cost. So definitely, if we define or if we bound the cost per operation as this thing, that will give us a correct upper bound on the actual cost. Okay. So then we can say that the amortized cost. So if we look at a given type of operation, like an insertion or a deletion or a search, then it's okay for us to say that the amortized cost per operation of that type is what's the worst case of this quantity for that type of operation. Okay. Okay, so that was all kind of slightly abstract. So let's actually do this for something. Okay, so I said we're going to look at Fibonacci heaps. Before that, let's just refresh our memory on heaps. So example is heaps. So a heap is an abstract data type. What does it support? It supports insert, let's say, insert x, where it just inserts into the data structure. Let's say that x is the values x are comparable. So you can do less than and greater than on x's. There's some total ordering on them. You can also do delete min. Okay. This returns the min x. Let's say we have a heap h. The min x in h, and then deletes it. And then there's decrease key, which takes a pointer to some item in the data structure. Say p is a pointer to item. And this k is a key, is a comparable element. Okay. And what this does is replaces that key at pth item, at item p is a pointer, with k, which must be at most p's current key. So this is just an abstraction of the kind of data structure you would need to implement, for example, Dijkstra's algorithm. Okay. Remember Dijkstra's algorithm? For each vertex, we insert it into a heap with key infinity, except for the thing we're searching for, which we give key 0. And then in a loop, we keep doing delete mins, and then the relax step is a decrease key, basically. So you can go revise your memory if you forgot. But this is exactly what Dijkstra needs. So Dijkstra, single pair shortest paths with non-negative edge weights. The runtime, I mentioned this last time, is O of n times, let's see, you do n insertions, you do n delete mins, n times insert, let's say time to insert, plus time to decrease key, plus m times time to do a delete min. Okay, where n is the number of vertices and m is the number of edges. Okay, so what kinds of, what's an implementation of a heap? Implementation of the heap data type. So we have binary heaps. Okay. That's due to Williams in 64. What does that give you? All operations are worst case log n time. Insertion time and delete min time and decrease key are all O of log n. Okay. We also have binomial heaps. I think these are due to Gilliman. Oh, Villaman. Oh yeah, and I should have checked. I do have a scribe, right? Yeah. Okay, great. Okay, and what does that give you? So these are now worst case. But from the if you're using your data structure inside some algorithm like this, you don't really care if your bounds are worst case or amortized, right? I mean, worst case is a stronger property, but depending on your application, you might not care. So good. So what does he get? He gets an amortized TI being constant. And let's see, decrease key. And also delete min log n. I guess that's actually a worst case bound. So the other two are worst case. So worst case t delete min and t decrease key are both log n. Question? The bound? Oh, m times decrease key. Sorry. Yeah. Yeah. Okay. So this is, I guess, a little better. And the worst case of t insertion, of the time to insert, is also log n. So in the worst case, it's no worse than binary heaps, at least up to constant factors. But the amortized insertion time is better. Okay, that's not enough to speed up Dijkstra's algorithm. But then there are Fibonacci heaps. I think that's from 87. Yeah. This is due to Fredman and Tarjan. You're going to see Tarjan a lot in this class. How did we see him already? No, I don't think we've seen Tarjan yet. But Fibonacci heaps, splay trees, we'll also see him for cache replacement policies. Okay. Okay, so what Fibonacci heaps, what do they give you? So they give you amortized insertion time as well as decrease key, or delete min, sorry. No, decrease key. Okay, being constant. And they give worst case, and also, what do I want to say? Delete min. Is log n. Okay. These are all amortized bounds. Okay, so Dijkstra actually gets faster because the log n doesn't multiply m. I'll say a little bit more. So I'm going to assume you know binary heaps, or if you don't, then you can look them up. they're not going to be relevant for what I'm going to talk about today. And they're not too bad to pick up. I'm going to actually cover binomial heaps just because I think the best way of understanding Fibonacci heaps is an optimized version of binomial heaps. Okay, you'll see, like, once you see binomial heaps, you'll see where Fibonacci heaps come from. And then I'll cover Fibonacci heaps. There are two more things that happened afterward, which I'm not going to cover, but I'll give you the pointers. One is Geert Brodel. Okay. This is in SOTA 96. What does he do? Gets all the same bounds as Fibonacci heaps, but worst case, not amortized. Okay, and it's not. And he uses. So okay, so yeah, so he gets that, and then there's a paper by Brodel, Tarjan, and one other person whose name I'm going to misspell, Lagogiannis. Then there's a Brodel, Lagogiannis, and Tarjan. That's just 2 years ago, stock 2012. Okay, so they get the same exact bounds. The thing is, there are sort of weaker and weaker models of computation. Like word RAM, you saw you can do lots of stuff, right? I have a question. So these, I'm going to tell you that these data structures, these three, are all comparison-based data structures. The only thing they do with items, with the keys, is compare their values. Okay? So why can't you hope to get, you know, all of these constant? Why should one of them? Why should delete min be log n here? Yeah, because of heap sort. You could always, if you have n items you want to sort, you could always insert them all into a heap, and then repeatedly delete min. So if all your items are, if all your running times are constant or amortized bounds even, you would have a constant time sorting algorithm, okay, which is impossible in the comparison model. But we saw that in word RAM, you know, you can do some things faster than in comparison, right? So there's this game in data structures of kind of getting bounds with the weakest model of computation, right? So once you get something in word RAM, you can ask yourself, did I really need the power of word RAM? Could I get it in the comparison-based model? Okay, or maybe all I need is like a random access in arrays and to array entries, but I don't actually need bit shifts and XORs, etc. Okay, so Brodel's solution uses, I think, random access in arrays. I don't think it really needs more than that. Maybe I'm mistaken. But this is actually just a pointer machine implementation. Okay, so they get same as above, just using pointers with no arrays. Okay, so I mean, as you're going to see, well, you're not going to see that, but you can implement this using arrays. It makes indexing your parent and children a little easier, but you don't really need them. Here, you're just going to see pure pointer-based implementations. Yeah?
So has anyone been able to do better using word RAM?
Yeah. Yes. So, right. So we saw, I guess, fusion trees and Van de Boas. So they, right. So the better of them gets, basically you can do every operation in, let's say, root log n.
So if you think of one of those as a heap, then
Yeah, you can use them to implement heaps. Yeah, and all your operations. So if you take the better of fusion trees and Van de Boas, you would get everything in root log n. Although what I presented in class was a static fusion tree. So it didn't support insertion or deletion. It just supported queries. And I guess if you're just searching for the min all the time, that's not really interesting. But there is a dynamic implementation of a data structure achieving the same bounds as fusion trees. So I asked last time who had seen Fibonacci heaps. Out of curiosity, who's seen binomial heaps? Okay. So let me just, so some people have, but many haven't. Let me tell you what binomial heaps are. And then from there, we'll see how to get Fibonacci heaps. Yeah.
I have a question about like the static structures.
Yeah.
So can you not use them to like sort? So you take like the largest. Oh, never mind.
Yeah. There's like the pre-processing phase that could be expensive. That's the problem. Yeah. Okay. Okay. Oh, and what else? Oh, yeah. Okay, good. So, binomial heaps. Oh, and I want to say one more thing, actually. I'll put one more reference up here. Who are these folks? So there's also a paper on the archive just this summer. So Kaplan, Tarjan, and Zwick on the archive this summer. So what do? So they don't actually improve any bounds. They just, so you're gonna see with binomial heaps. So okay, so for the people who have seen, who has seen binary heaps? Raise your hand. Okay, so almost everyone, not everyone, but a binary heap is a tree. It looks like a tree. Okay, as you're gonna see with binomial heaps and Fibonacci heaps, they're not trees but forests. Okay, we're gonna maintain all our items in a forest, in a forest-looking thing. They show how to get the same bounds as Fibonacci heaps where you never have a forest, like it's always a single tree. Okay, so just so there are like just different variations on making things simpler to implement or nicer for whatever reason. So I'll just say also see that paper if you want. Okay, but there are no improved bounds in there. Okay. Yeah, I guess part of the issue is Fibonacci heaps are known as having somewhat, large constants, so you wouldn't actually use them in real applications. So then now people are trying to simplify them in various ways and hope that one day they'll get Fibonacci heaps people will actually use all over the place. So, okay, so binomial heap. So we'll maintain. So each item is a node, and we maintain these nodes in a forest. Okay, and also, if x is the parent of y, then the key of x should be at most the key of y, just like in binary heaps. So for example, you could have 5, 7, 22, but you couldn't have a 7 up here and a 5 below it. That's okay. Now, for a tree in our heap, its rank is the degree of its root. Okay, and what we're going to maintain is that, and also a tree with rank k will have exactly 2 to the k nodes in it. Also, for each k, we'll have at most. So very soon I'll start drawing a picture, and then this will be very clear what I'm talking about. For each k, we'll have at most one tree of rank k. And also, the root of rank k has k subtrees, and each and these are trees of ranks 0, 1, up to k minus 1. Okay, so let's just draw a picture. So what does a rank 0 tree look like? A rank 0 tree just looks like a node. A rank 1 tree, well, I have degree 1. Okay, the root has degree 1. And this is now a rank 0 tree, which is just by itself. A rank 2 tree, it has a child, which is a rank 0, and a child, which is a rank 1, which means it looks like this. And a rank 3 looks like this. That's a rank 0 child. That's a rank 1 child. And this is a rank 2 child, which means it has a rank 0 child and a rank 1 child. Okay, so that's, and remember these keys should be stored, like as you go from any node to its parent, numbers should decrease. Okay, so that's what it looks like. Good. Now, how do we do the operations? So decrease key is the easiest. We're given a pointer to some element, and we're told that we're decreasing its key. We do the usual thing with binary heaps. We change its key, and now it might violate the heap order property. It might be smaller than its parent. If so, we swap it with its parent. And if it's still smaller than its parent, we swap it again. And we swap it up the tree until it's in the right place. So change the key. Then keep swapping upward. As necessary. Okay. How about inserting an element? Again, we'll store, maybe this is actually what our binomial heap looks like. So we'll store all these roots, in a linked list or something. In a doubly linked list. Okay. So what do? We take x, and we just add it onto this linked list. So now here's our value x. Okay, we just inserted x. But now we're violating our property that we should have at most one tree of rank k, because now we have two trees of rank 0. Okay. So what do? We basically do binary addition, right? So you can write a bit vector where you have a 1 in the kth position if you have a tree of rank k, and you have a 0 otherwise. And now we're like adding 1. We just added one element, so we're adding 1 in binary to this number. Okay, so 1 and currently our data structure looks like we have a rank 0 tree, we have a rank 1, we have a rank 2, we have a rank 3. And now we're adding 1 to this number, and that's going to give us 1, 0, 0, 0, 0. Okay, so what's going on here? Well, we're going to merge these two. Okay, so let's say x happens to be bigger than that element. So x will get moved here. Oh, now we have two rank. So now there's a carry. we have two rank 1 trees. We need to merge them. One will be the child of the other, just depending on the roots. Okay, so for example, maybe this guy hangs off here now. And then now we have two rank 2s. There's a carry. We add them, et cetera, until finally this will all merge into a rank 4 tree. Okay, so add a new singleton tree to forest. Then repeatedly merge trees of equal rank. And delete min is very similar. Delete min is as follows. Okay, so one of these roots, let's look at this picture. One of these roots is the minimum. It could be any one of these roots. So let's say that's the minimum. Okay. So what do? We return it, we delete it, and all its children now become roots. All of these children become new trees in our forest. And again, it's like binary addition. Right? So we have to merge things of equal rank. And what ends up what trees do we have? Well, we have the trees that correspond to binary adding this number, namely, so we have this is basically 1, 1 to what's left up top. Okay, so delete min is remove the root of some tree, namely the minimum, and insert all its children as roots in the main forest. Yeah.
Would it be better to have like a meta tree or something so we wouldn't have to search through all the roots? Or
Well, I mean, so we're only shooting for a better amortized bound for insertion, and because a rank k tree has exactly 2 to the k nodes, we know that the highest rank possible is log n. And also because we know that there's only at most one tree of each rank, that implies that there are at most log n trees in our data structure. So, finding the smallest guy will take at most log n time. We can just check all of them. Yeah. Okay, so good. There's roots in the main forest. Now merge equal rank trees. Okay, good. So what's the worst case time? So I said we're shooting for insertion taking constant amortized time. What's the worst case time for an insertion? Log n, right? Because we could be in a situation like this where, we have a tree of every possible rank up to log n, and then we'll have to keep repeatedly merging as we have these carry bits. Okay, so it's true for all of the operations. In the worst case, all operations take log n time. We want to prove a better amortized bound. And we're going to do it using the potential function method. Okay. So remember, we're going to bound the amortized cost per operation by the actual cost. Okay. plus the potential difference. So we need to define a potential function, which is always non-negative, and so it takes as input a state of the data structure. Okay, so if we're looking at a picture of the data structure, does anyone have any ideas of a good potential function? Well, first of all, tell me this. What's the time it takes to actually do an insertion? So, I mean, log n is the worst case, but say it in terms of what we're actually doing. The smallest rank for which you don't. Yes, that is true. That is true. Okay, so maybe right, which is yeah. So I think that's right. Yeah. The number of trees you already have. That's right. So let me just say something. So the actual cost. Let me say actual cost of an insertion is big O of the number of trees we have. Let's say, yeah. So let's say t minus t, which is +1. This is the old number of trees. This is the new number of trees. Okay. So I'm going to define the potential of the state of the data structure to just be the number of trees. Okay. And now let's look at the cost of an insertion. Remember what I said it is. It's the actual cost plus the potential difference. Okay. And let me see, this big O is, let me just ignore the big O for now. There's some, say, constant times this. So I could put a constant on the outside of this and then put the same constant there. That's not really going to matter so much. So the actual cost, this is the actual cost, plus the potential difference. So the actual cost, we said, was t minus t plus 1. And what's the potential difference? Oh, and what do you know? Okay. So that's it. And you could look at also the amortized cost of the other operations. The actual cost will be certainly at most log n. I mean, for the others, we're just getting a log n bound. The actual cost is certainly at most log n. And the potential difference, I mean, you're never going to have more than log n trees anyway. So you're going from some number less than log n to some number less than log n. So the other operations also, with this kind of calculation, we're bounding them by log n too. Okay, so that's basically it for binomial heaps. Okay, so now I want to get into Fibonacci heaps. So what are Fibonacci heaps trying to achieve? So they're trying to achieve constant time insertion and also constant time decrease key. Okay. So the main idea of Fibonacci heaps is to be lazy, okay? Which is the main idea behind a lot of amortized data structures, and don't really do work until you're at the point where like you really have to do it. Okay. So one example of being lazy is, so wait, so delete min is going to take log n, decrease key should take constant. That's right. So one idea to be lazy is, first of all, why, so as soon as we do an insertion, we enforce that this thing holds, right? We do merges as soon as we do an insertion. There's no real reason to do it. I mean, if all we do ever in the data structure is insert, then why bother doing any work? Just like add that element to the top of a add it to a linked list. Okay. I mean, the only reason we do this merging thing is so that the other operations are faster. Like, for example, a delete min. So why don't we just make the delete min do all the work? So there'll be lots of nodes up in this top linked list, lots of trees. And when the delete min comes along, he'll consolidate everything when he gets called. The insertion doesn't have to do it. There's no reason for that. So there's no reason for insertions to spend time consolidating. Do all consolidation during delete min. Okay. But it's not delete min we're trying to speed up, it's decrease key. And it looks like decrease key is in bad shape, right? I mean, if you're in a tree that has big rank and you're doing this bubble up stuff, then you're going the height of the tree, which is log n. So if someone keeps doing decrease keys over and over again in the large rank tree, then we're out of luck, right? And they can do that. So what's something extreme? I mean, it's not going to work, but just tell me something ultra lazy that you could do to implement decrease key. I want decrease key to take constant time. Yeah.
Just like put it back on the linked list.
Yeah. Just so if I want to decrease key, on like say this guy, let me do someone that actually has some children. Let's say I want to decrease key on this guy. I'll decrease his. So first of all, I'll update him. Okay, and if he doesn't violate the heap order property, that's great. I don't have to do any bubbling up. But if he does violate the heap order property, I'll just cut this edge and just put him up as a tree. Okay, great. So really lazy decrease key. But it's the right idea to first start off really lazy and then figure out if you need to do more. Just do the bare minimum to get the job done. Really lazy decrease key is decrease x's key, and if x now is smaller than parent, cut x's tree out and place as a top level tree in our linked list. Okay, so unfortunately, being this lazy is not going to get us the desired bounds. It can be pretty terrible. Okay, and the main reason is, so what was the actual cost in binomial heaps? What was the actual cost of a delete min or let's say a delete min, the actual cost of a delete min? This is not a trick question. So what was the cost of a delete min in a binomial heap? What does a delete min do? It has to look through all of those top level roots, find the min. So let's say that the maximum rank in your tree is k. It looks at k different roots, finds the min, then deletes that out of the tree and then puts the children in and then merges things. So in terms of k, what's the worst case running time? K, right? So of k. And what was the argument that we said for why? So what k is at most what? What's the worst case for k in a binomial heap? Log n. And why is that? What was the justification for that? Yeah, each tree is of size 2 to the k. We only have n items, so we can't have a tree of rank bigger than log n. But the problem is that if we start with this, if we use this really lazy decrease key, then we could have a tree of rank k that has a lot of stuff hanging off of it. Well, I guess nothing's hanging off of that, but over here, a lot of stuff is hanging off. And then we did a bunch of decrease keys on all these guys. We decrease key all these roots. Let me not decrease key them exactly. Let me decrease key their children. Oh, OK. We decrease key all of these guys. And what we're left with at the end of that is a tree of rank k that has exactly k plus 1 items in it. Right? So our previous argument that rank k trees are big, therefore the largest rank in our tree is small, therefore delete min doesn't take too long, is bogus now. Okay? And so really what's happening is this guy, he's rank k and he thinks his tree is big, but little does he know that he's losing all of his descendants. Okay? So we need to somehow convey to this guy that he's losing his children. Okay? Or his descendants anyway. Okay? So here is the one extra thing that Fibonacci heaps do. Okay? Which is if P loses, let's say if node P loses one child x due to decrease key, no problem. Okay. But if P loses a second child, we cut P out of the tree too. And we make P's tree a top-level tree. Okay? Yeah.
So when we do that, do we also propagate the...
Yes, this might recurse. So P itself has a parent. And P might be the second child lost by its parent. And its parent will then cut itself out of the tree. Okay?
I was really asking,
Yeah.
when we do this,
Yeah.
we also modify the key at that node? So like if decrease key decrease the child's key
Yeah.
so that it gets cut out,
Yeah.
do we now do the swapping when we cut P out? Or do we cut P out as a separate tree to the child that it lost? Or
Oh, so yeah, okay, so to answer your question, so let's say P loses a child x, that's the first child, okay. It now loses another child y. So y's subtree is now a main tree in the top level. And then separately, P and what's left under P will be another tree at the top level. So P and y will no longer live together in the same tree. Does that answer your question? Okay. Okay, so now let's take a look at what a tree of rank k can look like in a Fibonacci heap. So let's say the rank is 0. Okay, it'll look like this. If the rank is 1, it looks like this. And this is what it would look like if it were a full rank 1 tree, like in a binomial heap. But then, this we can't then cut out any children because it wouldn't be a rank 1 tree anymore. Okay. How about a rank 2 tree? Well, it has 2 children, and this one is a rank 1 tree. Okay, and now this is what it would look like if it were full. But we could have done a decrease key at some point in the future. We could have done a decrease key on this element, and then now this gets cut out and made a top-level tree. So it's possible then to lose. Is this visible? I don't think this thing is that visible. It's then possible to lose this part. So let's say that the size of a rank K tree, the size here is 1, 2, 3. How about a rank 3 tree? So that's what it would look like if it were full. But then we could start cutting things out. So maybe this guy got decrease keyed. Okay. And now maybe this guy here got decrease keyed, so we lost all of this. Now, this guy here, we can't afford to decrease key him, because then this guy would cut himself out of the tree because he lost 2 children, and then the rank wouldn't be 3 anymore. Okay. So I think this is the most that we can cut out of the tree and still keep it a rank 3 tree. And the number of nodes left is 1, 2, 3, 4, 5. Let's just do one more. How about if we had a rank 4 tree? So it has 4 children. This guy looks like this. This guy looks like this. And this guy is a rank 3 tree. So he has 1 here. This is a rank 2 tree. Did I do that right? I have 1 more node than I'm supposed to have. Where did I insert an extra node? This? So this should have been a rank 3. So this is a rank 2. Ah, okay, good. So contract this edge. Yeah, okay, good. So, okay. Okay. So now that's a proper rank 4 binomial tree. Okay, so now let's try and cut out as much as we can cut out and still keep it a rank 4 tree. We can cut this out. We can cut this out. Okay. We can cut all of this out. And we can cut, I think, this out. I think that's all we can cut. And we're left with 1, 2, 3, 4, 5, 6, 7, 8. Okay. So there's a pattern here. Okay. Right. As you might have guessed, a rank K tree has, well, it depends on where you start indexing Fibonacci numbers, but it has at least the K plus 2th Fibonacci number as its size. Okay. So great. So anyway, we need to put all of this together. We need to actually prove something, okay, instead of just talking about ideas of how to be lazy. Okay, so the claim for amortized T of insertion and T of decrease key are both constant And T of delete min should be O of log n. Okay, and how do I know that a node should be cut out when it loses a child? So for each node, I'll just keep track, 1 bit, have I lost a child yet or not? Okay. And when I do cut myself out, I'll reset that bit. Okay. So it doesn't stay. So that's usually called the mark bit if you read the paper or read other people's descriptions of Fibonacci trees, Fibonacci, yeah, heaps or whatever. Okay, great. So proof. So first of all, just some notation. So let's say mark of x is 1 if x has lost a child and 0 otherwise. Okay. Then I'm going to define a potential function. My potential function on some state will be the number of trees plus 2 times the number of marked items. Let me just call this, I don't want to keep writing this, let me just call this trees of h, and let me call this number of marked items of h. That's going to be my potential function. So where do these potential functions come from? Usually you just try to, usually they're just engineered from trying to make a proof work. Okay, so you look at, what you do is you look at the state of the data structure and you say, after I do an operation, what changed after that operation? Well, the number of trees changed, and some things that weren't marked now get marked, and some that were marked get unmarked because I cut them out. And then you try and engineer these constants or engineer some function here to make everything bounded by what you want. Okay, so it's something that will make sense, I guess, in hindsight. But the intuition is basically a lazy binomial heap. Okay, so now let's bound some costs. Question? Okay. Insertion. So what's the actual cost? Remember, what do we do for an insertion? Do people remember? We're being super lazy here. We're just adding it to the top level linked list. So the actual cost plus the difference in potentials. So the actual cost is a constant. And the difference in potential, well, we have one more tree. The number of marked items hasn't changed. So this is 1. So this whole thing is a constant. Okay. How about delete min? Again, we have the actual cost plus the difference in potential. So now, what's the actual cost? Huh? Say it again? Sorry. Yeah, yeah. Oh, right. So yeah. So that's yeah. So you have to go through the entire list. Oh, and also I should say in Fibonacci heaps, we'll keep track of where the min is as well. Okay. So, but I guess that won't. We don't actually need to do that because we're spending that amount of time anyway. But so yeah. So the number of trees. So let's use this notation. Okay. So we have to spend t time. Okay. And good. So what's now the difference in potential? I'm sorry? Okay, I have a question. So how much, the number of marked items, how much did that change by? Almost zero. I mean, so the guy we just deleted might have been marked. Maybe. I don't know. So it might have gone down by one, but that's like, that's lucky. I mean, yeah. So let's just say it's certainly at most zero. So the difference in, let's say plus the difference in the number of trees plus the difference in the number of marked items, this is certainly at most zero. No one's being marked or not gets changed by deleting the min, and the min himself might have been marked. Who knows? Okay, the number of trees though, that's t minus t. So this is going to be at most, let's say this is O of small t. Okay, but so remember, when we actually do the consolidation during a delete min, we will enforce the previous binomial heap constraint that at most one tree of a given rank exists. Okay? So we know that we have at most one tree of each given rank, and we didn't prove it yet, but we're going to prove that sizes grow like the Fibonacci numbers. Okay, and Fibonacci numbers grow exponentially. Okay, so this will be O of log n. Right, because if we have a rank k tree, that means the tree has size at least f sub k plus 2, which is exponential in k, so k should be at most log n. Notice I didn't actually, that's just a picture. I didn't actually prove it formally. We'll, it's a very short proof. We'll see it at the end of this. And now decrease key is the last thing. So case 1, x doesn't get cut out because maybe the new key we gave it doesn't actually violate the heap order property. Then the actual cost is a constant. The difference in potentials, we don't change the number of trees, we don't change the number of marked items. So actual cost is a constant, plus the difference in potential is 0, so this is just a constant. Now case 2, is we do some number. I didn't really have to split it into cases like this now that I think about it, but we do some number c bigger than 0 of cascaded cuts. When I say we do c cascaded cuts, I mean we cut x out of the tree, and then now because its parent was marked, we cut it out of its tree, and then its parent was marked. We do this c times. There are c levels of cuts that we do. Okay, so what's the actual cost? So the actual cost plus the difference in potential, we can split that into the difference in the number of trees and the difference in the number of marked items. So plus the difference in the number of trees, I said T of H, plus the difference, twice the difference in the number of marked items. So what's the actual cost? C. Say O of C. Now let me just skip all these O's. So C. What's the difference in the number of trees? The difference in the number of trees is C. Right. And how about this thing? So, okay, so first of all, yeah, so what's that? So yeah, so this is, if you include the 2, minus 2c, let me just think for a second. Do I believe that? So, am I off by 1? So minus 2c, but I feel like I might have to add, so if I cut an item, it's, oh, I see. So if I cut 1, I clear here's mark bit. But then, yeah, I think there's an extra 1 maybe or something, right? Like let's say I cut x and that's the only thing I cut. Okay? Maybe plus 2. Let's say C is 1. I cut x and he's the only guy I cut. So now that means his parent was not marked before. So his parent is now marked. But now x's marked bit can get cleared. Okay? So I haven't actually changed the number of marked items. Okay. Right.
Wouldn't you move x regardless of its marking amount, though?
Oh yeah, sorry. So, but yeah, so yeah, I move x, but its marked bit gets cleared when I move it. Oh wait.
It might not have been marked.
Yeah, it might have not.
But it might have been. I just want to say it's at most. Yeah. Yeah. So yeah. Oh, and what do you know? Okay. So yeah, that's Fibonacci heaps. There's not really anything else to say. Questions about anything? Yeah.
What about the delete min worst case? That's open, right?
Delete min worst case. Yes, it could be linear because we could have done n insertions and our whole data structure will be a linked list. That's right. Yeah.
Sorry, can you explain the intuition for the potential function again? I don't really see how it's helping us.
Oh,
It seems a little bit arbitrary.
I mean, okay, so, right, so you're asking how do you design potential functions?
Or like, what is it actually helping us do? It just seems really arbitrary that we define some like definitions and then the numbers cancel out.
Okay, so what you should think of potential functions as doing are when we do work at some point in the future in the data structure, we want to charge the work we did to some previous operations. Okay? So we want to say the reason, so like for delete min, we might spend n steps doing a delete min, but we can only do those n steps in a delete min if there were n previous insertions that caused us to do this. And once that delete min happens, everything gets consolidated. So basically we want to say that those n steps in delete min were charged to n different insertions. So you should think of maybe the potential of the data structure as like a bank account. Okay? And when someone does an operation, they might deposit money into the bank account, which is what an insertion does. An insertion deposits 1 into the bank account because it increased the number of trees. And then later people are allowed to spend some of the money that's been deposited. Okay, so they don't have to pay for it themselves. So I think maybe that's the right way to think about potential function arguments. Right, so I guess insertion increases the number of trees, and delete min spends that, but let's see. I guess decrease key both well, sometimes decrease key deposits marks as money, and sometimes it spends the marks. Right? If there's no cascading, it deposits a mark, and then it can spend it in a future decrease key. Yeah.
Couldn't we have chosen that coefficient to be something really high, and then we would have been able to, I mean, like, why choose a, like a tight coefficient?
Oh, but I mean, we still want, so the cost of an operation is what's the worst case that this could ever be? What's the worst case that the actual cost plus delta phi could ever be? Okay, and in the worst case, it could be that C is 0 and then it's constant. Does that answer your question?
Well, it seems like we never used that 2 anywhere except here, right?
Yeah.
So, okay, so it happens that 2 works, but it's like the coefficient isn't really that important.
The coefficient of the 2? I mean, as long as you pick something that's at least 2, it would work. That's right. Are you worried because this looks like it could be negative?
I don't know. I'm just, it just seems like very.
I mean, it's somewhat arbitrary. There's not just one right potential function. The main thing that we needed was that in the potential function, this coefficient should be at least twice that one. Yeah. Yeah. Yeah.
So it's two additional trees, so your potential is going up by 2, you added 2 trees, and it's going down by 2, and you move mark item.
Right.
That's why you need 2, so that it doesn't split out.
Right.
And it's not actually a problem to make it bigger than 2, because you can never have, you can't remove more mark items than that.
Right. Yeah, it's not a problem to make it bigger than 2. Right. Yeah.
But it's just that it's elegant that it's 2 because they just can't split.
Right. Any other, yeah.
Yeah, what does it mean if it's like, oh, negative something?
I mean, then we'll say that the amortized of this operation was negative, but I mean, usually when we say that a particular kind of operation has amortized cost blah, we mean that in the worst case, the amortized bound will be blah. So in the worst case, C could be 0, and the amortized cost would be a constant. Okay. Yeah. Oh, did you have a question?
Oh, I was just not sure. Like, maybe we should have a really constant factor in front of the T for some reason, because like if you're consolidating everything, it might cost you not like T or something.
Yeah. So
It doesn't matter, right?
so everything,
Multiply.
all the actual costs have big O's here,
Yeah, yeah.
which hide some constant C, and then you would multiply this whole thing by C. Yeah, that's right. Okay. More questions? Yeah.
Is there any constraints on how you can make your potential function?
So I mean, what did we argue in the beginning about potential functions, about this amortized analysis stuff? Basically, to make it work out, we only needed that phi of the empty data structure is 0, and phi is always non-negative. As long as those two things hold, then your amortized bound you prove will be an upper bound on the true cost of a sequence of operations. Yeah.
It might be a little funky on the spot, but just to like help see if I can find these potential functions, could you like find a different potential function for the logic tree besides this one that works nicely?
Besides this one, so you mean other than changing the coefficient in front of that? So I wouldn't know how to formalize the statement that this is the only one that works, but no, I don't. You mean something else that looks sensible but is somehow conceptually different? I don't know one off the top of my head. Yeah. Other questions? Okay, so we have 2 minutes. I guess I'll just say next time we'll look at splay trees. That's a kind of binary search tree. It gets the same job done as like a balanced binary search tree in terms of log n time per operation, but it will be amortized. So in the worst case, splay trees could take linear time to do a query, but in an amortized sense, it'll be log n. But they have a bunch of other amazing properties. One such amazing property is what's called static optimality. Okay, so people who have taken 124, who took it last semester, have seen it. Otherwise, maybe you've seen it, maybe you haven't. Suppose I give you n keys, and for each of the n keys, I tell you the frequency at which that key is searched for. Okay, and then I tell you build a binary search tree which minimizes serving queries on this set of items with these frequencies. Okay, so you can do this using dynamic programming. You can build the best tree. Like, what do I mean by that? So a tree like this, a perfect binary tree, is great in the worst case. But if you have additional information, right? If you're told that I always search for one of these two items, then let me color them. Then those people should be at the top of the tree, right? Okay. And then everybody else you don't really care about. They can be wherever you want. I don't know. And you can make funny shapes. You can make it be like a perfect path, right? Or like you can make it look like this. So it's really, really imbalanced, just kind of going down like that. There are like sets of frequencies where this is the optimal tree to build for that set of frequencies. Okay, so the amazing thing about splay trees is that if you keep doing queries on them, they keep adjusting themselves after every query. They don't know the future. Just given the query you just asked, they'll adjust themselves. And if you ask what's the cost of serving an entire sequence, they'll do just as well up to a constant factor as the tree you found using dynamic programming, which was optimal for that set of queries. Okay, so they balance themselves to achieve this what's called static optimality property. But they have other properties too. Okay. Great. So we'll see splay trees next time, and I guess that's everything. And please sign up someone for September 30th to scribe. That's a week from Tuesday. And fill out the poll on Piazza.